Your product already works. Someone adds one AI feature to it. Summarize this thread. It ships on a Tuesday. 10 people use it. It is perfect. Your service calls a model provider over the network and waits. The call takes 6 seconds and nobody minds because nobody is waiting behind anyone else. Nothing here is wrong. It is simply untested. Here is what happens when the same feature meets 10,000 people at once. Turn the dial up and things break. Not gradually, in 4 steps. The first step exhausts your threads. The second one meets the provider's rate limits. The third sends your bill somewhere you did not plan for. The fourth blows the tail while the average stays calm. 4 different problems, 4 different fixes. None of them is the previous fix applied harder. Every fix becomes a box, and the boxes stay. By the end, you have an architecture nobody drew in advance. Turn the dial to 100. Now those 6 seconds matter. Your service holds a thread for the whole call. 6 seconds of holding per request, waiting on someone else's machine. So concurrency is not requests per second. It is requests times duration. Divide your pool size by your call duration, and you have the real ceiling, not the network, not the model, the pool. Then the provider starts refusing you, and your client sleeps before it retries. That sleep runs inside the pooled worker. The pool drains further with no extra traffic at all. The slots go red one at a time until none are left. Every worker in the pool is now parked on a call that has not returned. The process accepts nothing. Real users get nothing. And the dashboard is green. The health endpoint is asynchronous. It never touches the pool. It runs on a different path entirely, so it answers in a millisecond and reports that all is well. The orchestrator believes it. It keeps routing traffic to an instance that cannot serve a single request. A health check that does not touch what real traffic touches is not a health check. It is a ping. The fix is not a bigger pool. A bigger pool holds more threads doing nothing. Stop waiting on the request thread. Accept the work. Hand back an identifier. Release the thread. Your service answers in milliseconds now, and it answers every time. The generation still takes 6 seconds. The difference is that nobody is holding a slot while it happens. The client comes back for the result. It pulls the identifier, or it opens a server-sent event stream and receives tokens as they arrive. Client visible latency is no longer tied to generation duration. Those are 2 separate numbers, and only one of them is yours. Be honest about what that costs you. You now own job state, and it has to survive a restart. A job in memory is a job you lose. You own reconnection. The client will drop, come back on a different instance, and expect its result. And you have invented a new way to fail. Work accepted and never finished. Nobody is waiting on a thread, so nothing errors. The job simply sits there, running forever, and nothing complains. Something has to notice. Queues, workers, and stale job recovery own the video on async AI architecture. Turn the dial to 1,000. Now the provider is the one saying no. And it is not 1 limit. It is 3, counted separately. Requests per minute. Input tokens per minute. Output tokens per minute. You can sit comfortably under the request ceiling and still be refused because your prompts are long. Cross any one of the 3, and you get the same answer back. 429. There is one exemption worth knowing. Cached input tokens may not count toward the input ceiling at all. A stable prefix you send on every call can raise your real throughput without raising your limit. So, you retry immediately and on every failed call at once. That is the worst thing you can do. You just added load to a provider that already said it had none to give. Every retry pushes recovery further out. Read the response instead. It carries a wait interval. It is telling you how long to hold. And know how the ceiling actually works. The bucket refills continuously. It does not reset on the hour or the minute. So a short burst can trip a limit your average sits nowhere near. Averages do not get rate limited. Bursts do. Stop letting the provider decide who fails. Put a limiter on your own side, set to mirror their ceilings. Count your own requests, count your own tokens, set yours a little under theirs, so you refuse before they do. Now, a call that would have been refused waits in your queue instead. Same work, same delay, completely different failure. Because now you choose. You choose who waits and who is turned away, and you choose it before the request ever leaves. A hard downstream error becomes a local queue wait under your control. That is the whole trade. The provider's no is final. Yours is negotiable. A limiter alone is not enough. It decides how much. It does not decide whose. One queue, ordered by a rival, and a single caller can ruin the day for everyone. They submit a burst of 1,000 jobs. Every other caller sits behind all of it. Give each caller its own queue. Serve them in turn with a budget per round. The pattern has a name: deficit round robin. And charge that budget in tokens, not in requests. A long document should draw down the share of the person who sent it. Nobody gets starved. Nobody gets to take the whole thing. Per-tenant quotas and noisy neighbors own the video on multi-tenant AI. Turn the dial again. The load doubles. The bill more than doubles. Nobody billed you for a request. You were billed for tokens, and your tokens are growing. The feature got more ambitious. You added the last 10 messages for context, then the thread title, then a few examples to steady the format. Every one of those rides along on every call, for every user, forever. Output is worse. Output tokens are typically priced above input tokens, and your summaries got longer too. So cost per user climbed while your architecture stayed exactly the same. Traffic scales the load. Ambition scales the bill. Two levers and they compound. The first is a cache. Some of this traffic you have already answered. Serve it without calling the provider at all. A call you never make costs nothing. The second is a cheaper tier. Not every request needs your largest model. Route the easy work down to a smaller one. Keep the frontier model for the work that earns it. They do not cancel. The cache removes calls. The router makes the remaining calls cheaper. Another video goes further on cost, cutting an LLM bill without making the product worse. Now, the honest part. A semantic cache matches on similarity, not on equivalence. A question that is close but not equivalent gets served the neighboring answer, confidently, with no error. And the user believes it. Your dashboard says the average response time is fine. It is. That is the problem. The mean sits inside your SLA. So does the median. P50 is healthy, and P50 is most people. Now look at P99. It is well outside. One user in 100 waits far longer than your target says they should. That user does not know they are a percentile. They know the button stopped working. They are the one who files the bug and writes the review and tells their team. An average is a promise you made to nobody in particular. So where does the tail actually live? Almost never in the model. The model is not suddenly slow for one user in 100. It is time spent waiting in your own queue before the call was ever made. It is a cold cache, so the whole prompt gets processed from scratch. It is a slower region because that request routed somewhere further away. And sometimes it is a proxy that buffers the streamed response. Your server logs a healthy first token time and moves on. The client is still waiting with nothing arriving. Each of these is a different cause. Measure them separately or you cannot tell them apart. 2 moves and you need both. First, bound the wait. Pick a number from your SLA and refuse to exceed it. Second, decide where you go when you hit that bound, because a timeout on its own does something almost useless. It turns a slow answer into a fast error. The user did not want speed. They wanted the summary. Failing quickly is still failing. So the timeout fires and you fall through. A cached answer. A smaller model. A shorter summary. Anything you can hand back. A bound with nowhere to go is just a faster way to disappoint someone. This next one is not a threshold. Nothing you turn causes it. The provider stops answering, not slowly, not partially. The upstream, every one of those fixes sits on top of returns, nothing at all. And look at what you have. A limiter that decides who waits. A queue that holds work. A cache that answers, repeats. Not one of them generates a summary. Every fix so far assumed the provider answers. It also does not have to be total. Elevated error rates count. One region degrading counts. Half your traffic failing is an outage to the half it happens to. You cannot generate what the provider will not generate. So you reroute. The best version keeps the model and changes the channel. Same weights, different door, your prompts hold, your evaluations hold. Behavior is preserved. The other version swaps in a different model, and that is a real change. Different formatting, different refusals, different quality on the same input. So evaluate your fallback targets before you need them, and log every substitution. And route all of it through one control point. Then failover is a routing change, not an incident every team has to handle separately. The user gets a worse answer, on time. Say that out loud. Do not pretend it was free. The dial reaches 10,000. Nothing breaks. Walk the path a request takes now. A queue takes the work off the request thread, so no slot waits on a generation. A limiter mirrors the provider's ceilings, so the refusal happens on your side. Per caller lanes keep one caller's burst inside that caller's own share. A cache answers, repeats without a call. A router sends the easy work to a smaller model. Together, they hold the bill down. A timeout bounds the wait, and a fallback gives that bound somewhere to go. A gateway turns an upstream outage into a routing change. Now, the part that matters. Not one of those was specified in advance. Every one of them exists because something broke at a particular load. That architecture is right for this load. It is not finished. Turn the dial one more order of magnitude and new things break. The queue you added is one queue. At 100,000, it becomes the thing everyone waits on. The cache you added is one cache. Its own capacity and its own eviction rate turn into a ceiling. And one region stops being enough. Your users are not all near your servers, and neither is the provider. None of that is a flaw in what you built. It is the same lesson arriving again. An architecture validated at one concurrency level is not validated at the next. Not one box in that architecture came from a design document. Everyone came from a failure at a specific load. The pool ceiling gave you the queue. The providers gave you the limiter. The bill gave you the cache. The tail gave you the timeout. The outage gave you the gateway. So designing for concurrency is not drawing a complete architecture in advance. It is finding the next binding constraint, fixing it, and turning the dial again. That method does not care what your target is. It works the same at any number. That is the same feature that shipped on a Tuesday for 10 people. The call still takes 6 seconds. Nobody is waiting behind anyone else, and now that holds at 10,000. Nothing about it was designed in advance. All of it was tested into place. Build the small version, turn the dial, fix what breaks, turn it again. That is the whole job.